Okay. An account, maybe a CD or a bond, earns 5% interest annually. That's a lot. It's pretty good. At the start of 2013, $1,000 was put into account. Woohoo! Make a table of values to keep track of how much is in the account for at least 3 years. First, this word annually means each year. Okay. It means every year it takes the amount in there and then it gives you 5% interest on that amount for you putting your money in their institution. So we're going to need years since 2013 and money, right? How much is in the account? Money in the account. So in 2013, we start with $1,000 in the account. And then to compute the next one, well, I would do something of the sort. Okay, so 5% of $1,000 is equal to 0.05 times 1,000, which is equal to 50 bucks. Okay, so that's how much it went up for the next year. So in 2014, you start with $1,050. Okay, so I had to add that to it. But then in the next year, in 2015, it doesn't take 1,000 or 5% of 1,000. This is called compounding. It takes 5% of 1,050 because now that's how much is in the account. Okay, how much is that? Let's find out. So 5% of 1,050, $52.50. Okay, got it. So at the start of 2015, we will have 1,050 plus our interest, which is $52.50. So it will have $1,102.50. Got it. Okay. If we do this again, so 2013, 2014, 2015, 2016, we will be taking 5% of 1,102.50. And that is $55. And 0.125 cents, or I mean, and 12.5 cents. Looks like we're going to have to make a choice to round up or down now. We need to add that to the $1,002.50 that we already had in there. So add our interest, and we're going to round down to keep it safe because it's our savings account. We never want to overestimate how much is in our savings. I feel like that's a little bit scary for me because then I might spend too much. Oops, I said round down and then I didn't. Round down. Okay, even though this really does say to, logically we would round up, but in terms of this situation, this is a little more conservative with your finances. Okay, it says, is this model linear? No. This would be plus 50, plus 50, plus 50. So not a plus 50 each time scenario. Is it inverse variation? No. So when it has 0, it had an actual, so inverse variation has some number divided by x, but we have a 0 there. And so it can't, nope, no can do. Okay, so that's out. And as one increases, the other one is increasing. So it doesn't even have the big, small, small, big pattern. And is it exponential? In order for it to be exponential, it would have to have a constant multiplier. Let's see if we can find one. Yeah. We would have to do the ratio of each to each. So 1050 divided by 1000, 1.05. $1,002.50 divided by the previous one, 1.05. Ooh, $1,157.62. It was actually 62.5, just saying. I'm going to add it in there just to make it pretty. 1.05. So what I'm seeing is that there is a constant multiplier or constant ratio of multiplying times 1.05. So is it exponential? Yes. The constant multiplier is equal to 1.05. Okay, cool. What is the initial value? The initial value is, you know what, I'm going to put that, let's see. Initial value was $1,000. And that, by the way, means it is the, I'll label it with initial, and that's the A in our model. What is the constant multiplier? Well, we just computed it actually, and our constant multiplier, which is equal to the B in the model, was 1.05. What does the constant multiplier mean in the context of this situation? So here's what was happening. At the end of each year, the account earns 5% of the, not the beginning balance, but of the balance that's in there. Okay. And that means, how about in addition to keeping what was in there, or what was in the account. Okay, so that means the money will be, or the new amount will be 100%. So that's keeping what was in it, plus an additional 5% of it. So each year you will have 105% of what you had the previous year will be the new balance of last year. The amount will be 100%, 105% of the last year. Yeah. So we have additional money in there. Okay. Write an equation that models this situation after a given number of years. Well, since 2013. So I would call this, I don't know if you want to call it M for money, V for value, C for cash. I'm going to call it A for amount in the account, just because that's where like business people call it. And the initial amount was 1,000. The constant multiplier was 1.05. So 1.05. And after a number of years, I don't know, you want to use Y for years or T for years, whatever. So my A is the dollars in the account. And my Y was years since 2013. Got it. How much is in the account after 10 years? Okay, I see that we're doing Y equals 10, Y equals 20, Y equals 30. Round your answers to the nearest dollar. Okay, so it looks like I'm using this over and over again. So let's look at that. Okay. In 10 years, the amount will be approximately, here we go. Okay, so 1,000 times 1.05 raised to the 10, oopsie, raised it. So I needed the exponent. I almost forgot it there. $1,628 and about 89 cents. Got it. What about 20 years? The amount will be about, okay, 1,000, 1.05 raised to the 20 exponent, $2,653 and about 30 cents. Cool. Yeah, usually we round down, just FYI. So I felt a little bit strange writing this because I rounded up. But okay, safer to make a 0.29 there. And let's go 30 years. So I'm gonna copy and paste this and turn it into 30. $4,321.94. About $4,321.94. Ooh, look at that. That's nice. How long does it take for the money in this account to double? Okay. So we have a couple of ways to do this, and I want to show you using the calculator how we can do this. We could use the equation, okay? We could plug, okay? So guess and check, I call that. We could use the graph. I guess I said a couple, but really I meant 4. And we could also use the table. I've had students use the table quite a bit. All of this kind of depends on having this model equation. Because right now, for it to double, well, it started at $1,000. So that means to double, that is telling us that the amount in the account is 2,000, and the why, we don't know. How long? We're not sure. Okay, so here's what I'm going to do first. I'm actually going to use the graph, okay? So when it comes to the graph, for Y1, I'm going to put our model. And for Y2, I'm going to put in 2,000. And then I'm going to use the intersect feature. Okay, so let me go through this. Okay. First, I noticed that my stat plot is on from something else. So I'm going to turn it off. Then I'm going to go back to Y equals. Clear that function. Start from scratch. For Y1, 1,000 times 1.05 raised to the X. In Y2, I'm putting 2,000. Okay, but now I'm going to have to zoom, and I'm going to need to find where they both. I'm going to try to do zoom. I'm going to start with zoom 6 for standard. We're not going to see anything because these numbers are big. And standard is 10 by 10. It is what it is. And then I'm going to try to do a fit just so that we might all see the same thing. So I'm going to go down and I'm going to put zoom fit because I want to see these values. I could have also gone to second format and picked, oh geez, they don't even match in the zoom fit. Bogus. Well, here's the thing. how far out do we feel like we need to go? What if we go out to, let's pick something random like 20 years. And we know that we need these to go at least to 2000. Okay, so here, I'm going to go back here. It is true that I could just zoom out, and then I just need them to meet on the screen in order for the calculator to find their intersection or where they meet. But instead of doing that, I'm going to go to second format. No, I don't like that. Quit that. Maybe it's, window. It's window. My bad. Window. The X minimum was 0. We started counting at time 0. I'm going to go up to 20 for the years since. I don't care what the scale is, but counting by 5s is fine with me. The minimum, sure, I don't care if it's 613. And the dollar maximum, I'm going to make it just a little bit bigger than $2,000, even though $2,000 is where we're needing to go. I'm going to make it 2,500. The Y scale, seriously, let's count by 100s. Okay, and now I'm going to hit graph. Okay. There we go. Now we can see where these two things meet and are equal to each other. So for that, I go second, calc, intersect, hit enter. The first curve is the Y1, which is the exponential. The second curve is my Y2, it's the 2000. And my guess at where they meet, I'm actually using the arrow to the right button and saying somewhere over there. And look, it says, and then I hit enter, by the way. The intersection is 14.2-ish. Lovely. So the intersect is, so Y is approximately 14.2. Got it. The table, I mean, you would just go second table, and then you would hunt for where they equal, which is right around there. Yeah, somewhere between 14 and 15, it's going to equal 2000. So you would have to plug. Plug would be some serious guess and check stuff. I'm not going to do that. I'm going to do the graph, and I'm going to do the equation really quick. So when it comes to the equation, the amount would be 2000 is 1000 times 1.05 to the Y. This is being multiplied by 1000. I'm going to divide both sides by that. So divide by 1000. Okay, so this will be a 2. This will be 1.05. And to undo these exponentials, we use log. So it's just what undoes it, okay? So on the calculator, I'm going to do log, and I'm going to put 105 in for the base, and I'm going to put 2 here. That's why I wanted to show it to you, because it's so funky. So logs, what they do is they hunt for the exponents. That is their job. We went to math, go down until you see that log base. Hit enter. Log and the base 1.05 for the constant multiplier. So 1.05 to what power gives us 2? And voila, about 14.2. Okay, so approximately 14.2. All right, so to put this in a good way, how long does it take for the money to double? Well, it's not going to happen in the middle of the year. So it takes 15 years to double the money. this amount of money with this amount of rate and this type of account. Okay. So that would be, and if this started in 2013, 2028 is the year you'd be waiting for. Oopsie, can't see it. Right on. Okay, so here is an example of where our money is growing. So we get to keep what we have in the account and we earn more every time. Now, let's see a situation where we have depreciation or decaying. So the value of a home has depreciating at a rate of 3% each year. In 2013, it was 100 grand. Is this linear? Well, I see this rate. No. So if this is anything like this one was earning 5% each year, which means you would take 5% of it and then 5% of that and then 5% of when new. So when we hear this and it says a rate of 3% each year or annually, this is not a flat thing where it's the same amount every year. It's a percentage of the new amount each year. So is this model linear? No. No, it is not. Okay. No. Is it inverse? As one gets big, the other gets small, big to small, small to big. Well, it is going to go down. So it is big to small. This one's, but it doesn't have a second boundary. Like we are not dividing, so what I mean is we will be constantly multiplying instead of doing a division by our variable here. So this is actually out as well. And one way to help you with that is actually to make a table, but I am going to use the fact that in our last one, we did a 3% per year increase and do that here, but with a 3% per year decrease. So essentially, I'm going to hop till this step right here. And instead of having an increase, I'm going to make that into a decrease. So how can I tell? Well, I'm going to do 100%, take away 3%, makes 97%. And so I'm going to say, no. This is definitely exponential. And our constant multiplier is 0.97. Oops. Did not write what I said. 0.97. Okay. So that's how much we'll be retaining. We will lose 3% of the value each year. We will retain 97% of the home each year. What is the initial value? Initially, 100 grand. What is the constant multiplier? Well, we just wrote it down, so let's write it down again. Yeah. So the constant multiplier is equal to 0.97. Got it. What does the constant multiplier mean in the context of this situation? Okay, I already said it, but I'm going to say it again. It means the home loses 3% of its value each year. And retains 97% of its value. Write an equation that models the value of this. Okay. So here's what I see. The value of the home, I'll write V, okay, is equal to the initial 100 grand, okay, times the constant multiplier 0.97 to our independent variable, which is years per year. So I don't know, I'll use T for time. So T equals years since 2013 in this case, and V equals the home value in dollars. Got it. Predict the value of this home in 2013. Okay, so that means value equals question mark, time equals how much time has passed. 2023, take away 2013, 10 years has passed. So T is 10. Right on. Here we go. So the value will be approximately 100 grand times 0.97 because it's going down to the 10th. All right. 100,000. Retaining 0.97 of it for 10 years in a row. So that is approximately 73,742. It was a rough time for this home. Yeah. Okay. And use your model to predict the half-life of this home's value. Ah, okay. So half of its value will be 50 grand. Okay, so half. Okay, so that is actually the V, and we don't know when. Predict, use your model to predict, okay, T equals question mark. Okay, so there were two scenarios for this. I'm going to use the equation and the log to undo this on the calculator, or you could use, so if you use the graph table plug, or if you use the graph in Y1, we would put 100,000 0.95 to the X in Y1, and Y2, we would put in 50,000, and we would graph it, zoom out until we find their intersection, and use second calc to find their intersection. But I'm going to use the equation real quick. Maybe both. It's good to have a check. So if you're going to use the graph, those are the steps you would take. I'm going to try the equation here. So 50,000 is equal to 100,000 times 0.97 to the T. Divide both sides by 100,000, which should end up giving you a half, because hence the half-life. So 50 divided by 100, that'll be a half, and 0.97 to the T. And now I will do log. Okay, so the exponent on 0.97. So what is the exponent on 0.97 that will spit out 1/2? I bet this is a rounded answer. Here we go. Math. Go down to log base B, log base 0.97 of 0.5, and we get about 22.8-ish. So, or you know what, that looks like 3/4-ish, 22 and 3/4 of a year. I kind of like that. Years. Okay. If we were going to do it the other way, right? We really would need to go into y. We would have to put in 100 times 0.97 to the x. Nope. Delete, 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 enter. Nope. Did not like that. Delete that. Okay, that's fine. 50 grand. Window. Well, it has to be bigger than 22. We know that. Let me put in 30. We need it to intersect at 50 grand. So let me go below that and go 40. No, let's just go 20,000. And let's make that be 55,000. Okay. Graph. Oh boy. Oh, biscuits. What did I do? Hey, shouldn't that be 0.97? Yeah. Well, okay. Second calc. Intersect. First curve is blue. It's the exponential curve. Oh my goodness. No. I really put this in wrong. I got to start here. 100,000, 0.97 to the x. Okay. Yeah, I definitely made a mistake in punching it in, and I really just should have started from scratch. There's our curve, and there's our decay. As soon as I saw it, I was like, what? Okay. So it needed to come down for decay. Second calc. Sorry about that mistake. First curve, exponential blue. Second curve, 50,000 red. Guess. Oh, that's weird. My guess is right here. I'm going to hit enter. And the intersect, about 22.75 or 22 years and 3/4. So that's nice to have a validation or a check. Predict the half-life of this value's home. So what that is saying is let's see, after about 23 years, the home is worth 50 grand. Yeah. Oops. Okay. So let's just really quick talk about the difference between exponential growth and exponential decay, because they are similar, but they are not the same. One's going up, one's coming down. And let's write this in. I had something real specific that, here we go. I have too many papers on my desk. So when I think about the model for exponential growth and decay, or exponents in general, right? First, I think, okay, the model for exponential functions is y equals a times b to the x, where this is the response variable. A is the initial amount. B is the constant multiplier. And x is the explanatory variable. And in the case of exponential growth, if it's given in terms of a percentage per year, so we would do 100% plus R percent to get this constant multiplier when that happens. Otherwise, to get the constant multiplier, we are doing that ratio of new to previous. Okay. And then, kind of like what we did in example 3, where we computed these ratios and we got a 1.05 constant multiplier. And if this, when we're growing, this constant multiplier is going to be bigger than 1. So the constant multiplier is greater than 1 when growing. Okay. Because that means you have 100% plus additional, so it's growth. Now, when it comes to decay, we're going to see something similar. Let's see. When it comes to decay, it'll still be exponential. A times b to the x. So the response variable is still the initial times the constant multiplier that is repeatedly multiplied, which gives it an exponent variable. So repeated multiplication is represented through exponents. So that is all the same. It's just that now if it's decaying, if it's written in terms of percentages, we will be deducting that amount to find that constant multiplier, because it's going down or decaying, going away. It's only retaining, like in this one, it was only retaining 97% of its value each year. Okay. The constant multiplier is still this ratio of new to previous. Same. But when we're decaying, or when a model is decaying, the constant multiplier is a decimal that's less than 1. When it's going down or declining exponentially. Okay, so we have these 2 examples where, we had home value that was going down and decaying like this. And in this other one, we had savings where it was exponentially growing, where we added value each time. So what I look at to compare is kind of notice there's the initial value, and then this is bigger than 1, and this is lower than 1. So this would be a decay of 3%, and this would be a gain of 5% every year.